water divided by the total. So how many moles of water do I have? 4.50 moles divided by 8 moles. Right, because it's 3.5 and 4.5, so that's how you get 8. And then for water, it's 78 torr. So Vp of H2O equals, fuck is my calculator? There it is, my calculator. All right, so 4.5 divided by 8 times 78, so that's 43.875 torr. Now the unit that you get, all right, the unit that you get is going to be the same when you come out of there. So as you can see, everybody look up, when you change the mole fraction, you lower your vapor pressure. And what's the purpose of that? So you can raise the boiling point. Raise the boiling point. And that's very important whenever you have, a car, you want to have a high boiling point so it doesn't overheat. All right? Probably a better example. Cool. All right. And then the other thing is, now we want to find the benzene one. All right. So the mole fraction of benzene would be 3.5 moles divided by 8.0 moles times, what's the new vapor pressure? Oh, the pure one is 63 torr. So that would be 3.5 divided by 8 times 63. So that's going to be 27.5625 torr. So as you can see, it is lowered, right? Is everybody agree with that? We are lowering the vapor pressure here. Okay? So now what was my VP total? I have to add both of them, 43.875 torr plus 5625 torr. Okay? So that's going to be 71.4 torr. 71 is our closest answer, so we're good with that. C. Okay? Now you only add them, right? You only add them because you had what? Two solvents. You had two solvents. If they only gave you the vapor pressure of water, right? They took out the benzene part. So what do? What's the answer then if you took out the benzene? It would just be 43. Does everybody agree with that? That's how you know one or two solutions. Okay. All right. Any questions on that? Cool. Next we move on to the Van Hoff factor. All right. Now the Van Hoff factor explains why it is important to have ionic compounds in solutions. All right. It explains why you want to have ionic compounds in your solution, because it is supposed to raise the boiling point or lower the freezing point. All right. Raise the boiling point or lower the freezing point. Now, first of all, we need to find I. And I stands for things that are ionic. All right, so if somebody tells you what's the Van Hoff factor I, it's for things that are ionic. All right, so in general, if something is covalent, then what is I going to be? 1. Okay, now I just tells you the number of ions in the solution. So if I had NaCl, the I value is 2. Why is it 2? Right, because NaCl breaks apart into Na plus and Cl minus. So there are 2 ions in that solution. Now what about Na2SO4? How does that break apart? We would have 2 sodiums and an SO4 2 minus. This is where naming is important, because you must know that sulfate stays together because it is polyatomic. You right with that? So I would be 3 in that case. Okay? Now, you see that there are little estimates there. Is everybody got a little like about 1, about 2, about 3? The reason why is because this is just telling you how much it's supposed to dissolve. It says about 2 because you have 2 ions, about 3. But there is a real number there. In your homework, they might give you a real number. They might say I is 1.95. So what do? You fucking use that number. Right? That you don't sit there and say it's 2. You do 1.95. All right. So because I say about, because here what are we doing? We are guessing it. Is everybody good with that? So it's a guess that you're going to make. For things that are covalent, are they going to break apart? Are they going to break apart? No, they're going to stay together. So I is 1. All right, I is 1. Okay. Now, I'll show you where that comes in. All right. Now, this whole time, we are talking about adding salt to a solution, right? And what is the purpose of adding the salt? The salt is something ionic, so don't think it's just NaCl, a salt. So if we add a salt to a solution or a solvent, it is supposed to raise the boiling point and lower the freezing point, okay? Raise the boiling point and lower the freezing point. That's what it's supposed to do. Now, we've been talking about the idea, but now we're going to do it mathematically. We're going to figure out now what is the new boiling point and what is the new freezing point. Now, don't forget, folks, boiling point elevation, freezing point depression, okay? So here are the formulas. Delta TBP equals KBP times molality times I. Now, delta T is always T final minus T initial. KBP is a constant that must be given to you. It's not something that they're going to pull out of your ass. You got to be given it. M is the molality of the solute. So that's why we needed to know molality. I is the Van Hoff factor. All right? Now, a couple of things I want to point out. T initial is based on the solvent. KBP is based on the solvent. Okay? M and I, those are based on the solute. Okay? Because the molality are just like, if I were to say molarity, what's molarity? If I said 2 molar, that means the solute has 2 moles. Is everybody good with that? Same thing with molality. If I said 2 molals, that means the solute has 2 moles. Okay? So that's why I say it's based on the solute. I is again based on the solute, whatever you're putting in. All right? So this one determines what is your new, your final boiling point. This is based on the solution. Okay? So you got solvent, solute, solution. Because solution is both of them together. That's your new boiling point. Is everybody agree with that? Initially is where you boil. So what would be T initial for H2O if we were talking about the boiling point? What would be the initial boiling point for water? 100 degrees Celsius. So if I put salt in, what's going to happen? The boiling point will go up. So that's what we're going to figure out. Remember like that? But they would have to tell you a lot of other information as well to figure this out. Now, freezing point depression is the same formula. Okay, but why would they give me the same formula? Because they're crazy. All right? But really the difference is this. KBP is positive and KFP is negative. That's all. Because what does the freezing point want to do? It wants to lower it. That's why it's negative. And the boiling point is trying to raise it. Okay, so we're going to bring that up. All right? Now, be careful. Everybody listen up. Listen up. Because KFP will be given as positive sometimes. Sometimes positive, sometimes negative. But it always has to be negative. I know your professors might move the formulas around, but if you're using the same formula, these have to be true. Is it right with that? Like, I do my own thing, and I promise you this always works. Now, if you do your own professor shit, and then you come look at mine, it might be a little bit different, because there's 4 different people teaching this. All right, but I try to standardize it, and I keep it like this all the time. All right? Before you turn the page, don't turn the page, though. I want you guys to kind of use this little section. All right, and there's a reason for why I'm going to do that. Okay, compounds deals with IMF. Okay, compounds deal with IMF, and we generally say that if you have a high IMF, that means you would have a high boiling point, a high freezing point, okay, and a low vapor pressure. Those are the questions that they asked you before. So you had compounds like, NaCl, CH4. Now, a solution is different. Okay, so that's why, and you're going to say, well, okay, Rich, how do I recognize which one's a solution and which one is a compound? Well, in order to be a solution, you must have a concentration. So you agree with that? You must have a concentration. All right? Now, if you look at this formula, since K is a constant, what dictates how big T final is going to be? M and I. Does everybody agree with that? Right? If K is a constant, however big T final is going to be is M and I. Do we agree with that statement? Right? Because if you have a high MI, you have a high delta T. So that means you have a high T final. Correct? So we would go ahead and say if you have M times molarity, M or molarity, it should be or molarity, M or molarity. If you have a high M or molarity, that means you would have a high boiling point. And here's the trick, everybody look up. Low freezing point. Okay, because it's not the same one. Somebody might laugh over there, but this is the real shit. Okay? Somebody made this mistake before where they thought, oh, if it's a compound, high boiling point, low freezing point. But for compounds, high IMF, high boiling point, high freezing point. For solutions with a molarity or molality, high value of that times I, so sorry, it's supposed to be I as well because I and molarity and I is equal to a high boiling point, low freezing point, low vapor pressure, and a high P, which is called osmotic pressure. And we'll discuss this at the end, so, but I wanted to give you all of it now. All right? All right, because I don't want this to be a problem, okay? So if you have a high boiling point,